The book says we now come to the heart of the chapter. It frequently happens that studying some phenomenon on a vector space turns up a finite collection of subspaces such that the space is naturally isomorphic to their product. Under that isomorphism, injection after projection on the product becomes a family of maps on V, and the identities are reflected as they sum to the identity. Each composed with itself gives itself, and different ones composed to zero. Each subspace is one of their ranges. The definition, given a family of subspaces, sending a tuple of vectors, one from each, to their sum is a linear map from the product into V. If that map is injective, the subspaces are called independent. If it is an isomorphism, V is their direct sum. So V is the direct sum exactly when the map is both injective and surjective, that is, when the subspaces are both independent and span V. Restated. Every vector of V is uniquely expressible as a sum with one term from each subspace. Such an expression exists because they span V, and it is unique because they are independent. It takes both to have a direct sum. The book's example is a pretty one. In the space of continuous functions on the line, the even functions form a subspace, and so do the odd ones, and the whole space is the direct sum of the two. Given any function, averaging it with its own reflection gives the even part, and half the difference gives the odd part. The decomposition is unique because the only function both even and odd is zero. The even and odd parts of the exponential are the hyperbolic cosine and sine. Since injectivity is the same as having only zero in the null space, independence gets a convenient restatement. If one vector is taken from each subspace and they sum to zero, then every one of them is zero. For two subspaces, it is especially simple. They are independent exactly when their intersection is only the zero vector. So V is the direct sum of two subspaces exactly when V is their sum and they meet only at zero. Two such subspaces are called complements of each other. But a warning, a subspace does not have a unique complement. In coordinate 3 space, the only proper subspaces are the planes through the origin and the lines through the origin. If two proper subspaces are one plane and one line not lying in that plane, then they are complementary, and in 3 space those are the only non-trivial complementary pairs.